Okay, so now I'm going to talk a little bit more about 113D and then get into some other more technical stuff. First, I just want to say, 113D, it's a design class. It's more than a lecture. Only part of the time you're going to be sitting passively while information is fed to you. This is one of them, obviously, but that's only part of the time. And there will be some lectures, up to maybe 10 over the 2 quarters. Only a couple in the second quarter, and 8 or 9, maybe 8 this quarter. They're going to review a little bit about what you already know from 113, show you how to program the DSP, and give you some write-up and presentation tips. That's the idea of these lectures. It's also more than a lab. Early on, there will be, like in the first 4 weeks, there will be procedures and quote-unquote correct results. I mean, we know what you should be getting with the procedures. It's like a recipe, like a regular lab. Going to be lab reports, of course. But later, after that, for the mini projects and the real project, there will be no procedure, no correct results. Instead, the goals will be defined by, so for the mini projects, we'll give you some goals. But how you get there, that's going to be defined by you. You're going to be inventing. For you, you'll be inventing. It's not going to be new stuff in the world and all that. We'll save that for your... that and the Nobel Prize we'll save for your PhD work. But you will be managing a project. So that is something that you'll be doing a lot once you get out of here and into the world of work. Making a presentation and writing a couple of 3 reports. One of which will be in these IEEE transactions format. That will be the long project report. Okay, so yeah, like I said, the first 4 weeks, lecture and lab. After that, it'll be more like work. You're going to be taking on an assignment as part of a team. You're going to have a goal. They're going to be, milestones and weekly blogs. Well, we're going to ask you, especially for the project, to predict what you'll be able to get done by the end of week 3 and by the end of week 7. You're not going to hit it. But that's okay. Like I said, this is undergrad, this is college, this is you're here to learn. And we want you to understand what happens when people ask you how long it's going to take to do something. We want you to have some of that experience before you get asked that the first time out when you're working. All right. Your progress is going to be judged against the milestones and the goals. Well, yeah, especially against the goals. The milestones, if you don't get there, we'll give you a grade, but it doesn't count for much. And another last tip, cramming does not work in a design class. Those of you who took me in 3, I told you the same thing there. Cramming does not work for a project unless you enjoy pulling 3 straight all-nighters in week 10. No, this is not what you want to do. There's always more work than you think. So cramming does not work. You have to work on it each week. That's one of the other reasons that you're writing a blog each week. You got to have something to say. That means you got to do some work each week. Okay, yeah, like I said, if you put off doing the work on your project, you're going to regret doing it. So here's another last tip. This book here, whoops, dang it. What am I doing? Yeah, I'll get it. The C programming language, this is the 2nd edition, and it's ANSI C. It first came out in 78. Dennis Ritchie created C, and Kernighan basically wrote the book. So there's a case where division of labor worked out pretty well. But I love this quote by Kernighan saying, debugging code, that's harder than writing it in the first place. So if you're really clever in writing code, how will you ever be able to debug it? And that's a plea from Kernighan saying, keep it simple. Keep the code simple and direct and obvious to anybody. Because 1 week or 3 weeks or 6 weeks or a month, 6 months, you'll be looking at that code and saying, what was I thinking when I did this? So anyway, that's when you look at the clever code and you can't figure out what the heck happened. All right. So what is DSP? Well, okay, it's concerned with representing signals by a sequence of numbers and the processing of those signals. So you can have a vector, an array, you can have, you can be taking telemetry data from a missile. This is an EKG. Here's some image processing here. I forget what the guy's name that played Gollum. Anyway, he's instrumented, obviously, all of these sensors. A lot of signal processing going on there as well. I'll skip some of these. The processing is basically math operations, like filtering. That's one obvious thing. Here's Fourier transforms, one of the fundamental things that you do in DSP. This looks like a sine wave, and yeah, there's a peak, by golly, in the DFT, in the discrete Fourier transform. But you can see that the amplitude is dropping a bit as you move along, and yep, there's a second peak right there. So it's probably 2 frequencies rather close to each other. And you can see clearly here that this is probably on a dB scale, so this one is much, much smaller than this one. All right. Also, can't forget 2D FFTs. You're going to get to do one in a lab. So we're going to do 2D FFTs. And it actually is a representation of a physical phenomenon we'll talk about. It's pretty cool. And there are other math operations besides these, but these are some of the bricks and mortar of DSP, filtering, and FFTs. And this is just a quote from from Nikon, from the Wikipedia entry on their XSpeed image processor. That I've had this forever. This is getting kind of old, but clearly, computational photography is a big, big deal. I wish Nikon and Canon would get it, because Apple, and in particular, and then, Google, they are having them for a lunch. It's amazing what Apple and Google are doing with computational photography that, Nikon and Canon have done with lenses and, a whole bunch of hardware and everything else. And, it's just an amazing thing. And, more and more that kind of work is being done right on the device. So yeah, here it is right here. This is the iPhone 11, I believe. And you got 3 cameras and you're doing some real-time stuff. You're going to be taking a bunch of pictures and they process them. And there's about a 1 second time for the processing to happen. Have it done in 1 second. Take the picture, and 1 second later, your processing is done. All on the device. So this is the kind of thing that I keep talking about. Embedded systems. This is where so much work will be done, is in embedded systems. So jobs. What about jobs in signal processing? I think I forget the A, of course. I should have figured that. So you can type in jobs in signal processing, which obviously I've done before, and you get a bunch of you get a bunch of these things. 100 plus more jobs, and they're looking for usually they're looking for experience, but not always. Let's see, I think I want to go back. And I'll just slide down 100 more jobs. Come on, give me an answer here, folks. There we go. Oh, I guess that's where I wanted to be. So here's one, mid-level at Viasat. That's down in San Diego area, Carlsbad. Software engineer for radar, senior radar signal processing, so experienced digital signal processing engineers, signal processing, I think right there, that was the one that I've seen before, junior signal processing engineer. It's in the city of New York. Whoa. Okay, here's McDonald's wanting an audio signal processing engineer. Interesting. You know, so there are lots of them in here. Audio DSP engineer for Apple. You know, lots of different, you know, some defense kinds of things and others that are not. You know, I don't think McDonald's is a defense company. So anyway, lots of different jobs for people in digital signal processing. I just thought I'd show that to you. Let me go back to, whoops, that's not where I wanted to go. I want to go here. Okay. You know, and now this is getting to be a couple of years old, but right in the IEEE spectrum, desperate for data scientists. Yeah. Here's some other things, application of signal processing and machine learning. You know, what's the, you know, there's a lot of signal processing going on in machine learning, no question about it. You know, here's a real full band speech enhancement, connections between machine learning and signal processing, a couple of links here. You can check those out. This is the most common DSP operation right here, the MAC operation, multiply and add or multiply and accumulate. The MAC instruction. In a DSP, you can get done in one clock cycle what a normal computer takes 70. Now, I would expect that the H7 that we're going to be using, it doesn't have a DSP core, but it's got some special instructions. DSP instructions, and it's not going to take 70. It's going to be more than one, but it's going to be far fewer than 70 clock cycles to get this particular operation done, the MAC operation. I will point out to you from time to time when I'm talking about the things that have to be done. Here is a multiply and accumulate, just another example of where you will see it. It's all over the place. All over the place. Yep. And again, so here's what it says, you know, A equals B times C plus D, and, you know, E equals F times G plus A. So multiply, add, and accumulate. So, and I probably don't have to show this to you, but I will anyway. It's used for all kinds of audio processing. You know, this doesn't even mention music. Seismology, medicine, and of course in image processing, there's photo adjustments. That's all the computational photography that's going on with Mac and Google, or with Apple and Google. Mapping, medicine, digital communications, radar, sonar, just everywhere. It's used in lots and lots of places. Here, extraterrestrial intelligence nets. UC Berkeley, developing state-of-the-art instruments and digital signal processing methods. And here's the link, Scientific American link. Search for extraterrestrial intelligence. Okay, so a new subject, waveform generation theory. So this is going to take you back to 113 a little bit. You're going to get a table lookup kind of arbitrary waveform generation in the first week, I believe, in Lab 1. It will be the sinusoidal only, and you can do it by filtering. You can take another waveform like a square wave and filter the heck out of it and end up with a sine wave. Or you can use a second order system like today. By today, I mean in Lab 1, you will be using a second order system. So just to take you back a little bit, here is a complex plane, real on the x-axis image, imaginary on the y-axis, and the question is, to generate a sinusoid, we need an oscillator. So where in the complex plane will we find an oscillator? So if this were a live class, I'd stop here and let somebody try to answer this question. And maybe one of these days I will, but not this time. I'm just going to give you the answer. As if you don't know it already, you probably do. It's right here. It's on the y-axis. So you have only imaginary parts, no real part to the characteristic equation, that defines the system. And so and if you're talking about discrete, which is what we are, the previous stuff, this stuff is continuous here. We're talking discrete here again, but it's still it's a z-plane, but it's still it's a complex plane. But now you've got the unit circle, and if you're inside the unit circle, you're stable. If you're outside the unit circle, you're not stable. If you're on the unit circle, you have an oscillator. And that generates your sine wave. So again, I'm not that impressed by these figures, but still they tell the story. If you don't have imaginary parts, then it goes off exponentially. But if you have imaginary conjugates, then it goes off exponentially, but there's a sine wave that's expanding as well. Inside the circle, it's a damp sine wave that goes down to nothing. Anyway, so let's look at a second order system, and what's the impulse response of a second order system? You think about a tuning fork. What do? You bang, and the thing will sit there and it'll vibrate at a certain frequency. And so here is a second order system. And how do you know that? Because you've got n, y of n minus 1, and y of n minus 2. So you're looking back 2 places. That's a second order system. Well, a second order equation. The question is it a system? And the answer, again, I'd wait for an answer for you guys, but I'll just give it to you. No, it's not. You need the initial conditions. If you remember that from 113, you need the initial conditions in order to make it a system. So these are the initial conditions. And if you take that, if you write the equation like this and let b1 equal 1 and a2 equal to minus 1, you get this equation right here. Then what would you do? You would take the z transform. And once again, I'd ask you, how do you take the z transform? And if you remember, yn, the z transform would be what? It would be y of z, just like that. And if it's y of n minus 1, then there's a z minus 1, z to the minus 1 yz. And z to the minus 2 yz, that's how you take the transform. And then you just use algebra from there, because you want to get y over x. X is the input, y is the output. Here's your characteristic equation, and the roots of the characteristic equation follow this right here. And believe it or not, for any value of a that is less than the absolute value, less than 2, the roots are always conjugates on the unit circle. Always on the end. Here's a little MATLAB program that proves it. Right here, where I do an out plus and an out minus for the, it's plus or minus, obviously, right there. So, and when you go plus, you get this set of things, And when you go minus, you get this set of numbers. They meet at, well, you can say, well, okay. Then if you say, well, okay, I want this a value to be always less than 2, I can make that a cosine function, right? 2 cosine function will always be less than 2. And if I make the argument of the cosine function 2 pi f over fs, where f is the frequency of the signal and fs is the sampling rate, then you can say, well, okay, the sampling rate is 12 times the frequency of the signals. That means you're getting 12 samples for each cycle of the frequency. And that's great, you know, because it's following the sampling theorem and all of that kind of stuff, right? All you need is 2 samples per cycle or more to be cool with the sampling theorem. So anyway, so this is, you can call this theta. You could call this angle here, this thing theta. And theta then, and here's theta, the value for theta equals pi over 6, which would be what? That would be for a frequency where 2f over fs equals 1/6. So that would be like, if this is, if fs is 12f, so this would be 12f down here. So 2 over 12 would be 6. And the f's cancel. You're left with pi over 6. Put you right there. And you can let theta get larger and larger and larger until it hits pi, right? Pi. And at that point, what happens? What happens when pi gets to be larger than 180 degrees? Well, if you see that, that means that theta equals pi, right? And that means that, or theta is greater than pi, and that means it's greater than 2f over fs is greater than 1. And that means that the f will be greater than 1/2 of fs. And that violates the sampling theorem. And so what happens is that you get aliasing. You have violated the sampling theorem. You get aliasing. So that's what's going on there. So what you do is you write a little code. Now this is a MATLAB example, and so you can't do it like this in your in your embedded system. But this gives you the idea of it. The idea of it. Here's your sampling rate, and all this kind of stuff. You're simulating it actually. And so I'm calling it theta, is equal to this value, 2 pi f over fs, the 2 pi f fs ratio. And so this is what is, you're calculating this guy right here. So that's a constant. And you just evaluate it at a bunch of different values of time, which is, well, k, values of k for you're doing 100 points. And when you evaluate it, you get this value, you get the sine wave. The first point is the sine of theta. The first point is sine of theta. That's your impulse. That is the impulse input right there. Boom. And then that will always generate this waveform. Why is x equal to sine theta? X being the input. Remember, this is an impulse. This is an impulse, and it's time 0 only. When you bang the tuning fork, that only gets 1 input. After that, it just sits there and vibrates. And that's exactly what we're doing here. In the code, it gets used only 1 time. Here, in this expression right here, there's x. But after that, you're evaluating all of your y's down here in this loop. You never go back to this expression here. 1 time only. So why does it have to be equal to sine theta? So if you, there are a couple of ways of looking at it. You can evaluate a 2.5 kilohertz second order difference equation for 101 points. Let's start with an impulse of sine theta. So right there it is, right there. There's the impulse of sine theta. And you do it for 101 points. And you get this, all of these different points here. And note that I've connected the first 96 of them. Because why? Because the 97th point is the same as the first point, and the 98th point is the same as the second point, and the 99th point, you get what I'm saying there. And so what is that telling you? It's telling you that you've got your 5 cycles in 96 samples. So if you just do the math with the dimensional analysis, you will end up with this equation right here. 2 pi times 2.5 over 48 radians per sample. You could say, instead of 2.5 over 48, you could say 5 over 96. Multiply numerator and denominator by 2, 5 over 96. 5 cycles in 96 samples. Right? Okay. Or you can do it this way. You can say, well, delta t, I've got a sampling frequency of 48,000 samples per second. So the delta t is the reciprocal of that, which is 0.8 microseconds per sample, and the time in 5 cycles would be 2 milliseconds. 5 cycles at 2,500 cycles per second. The cycles cancel, you're left with seconds. The k is in the denominator, so that gives you milliseconds. And so you've worked it out this way with more dimensional analysis. You get the same answer, 5 cycles in 96 samples. 5 cycles in 96 samples. So that part is working correctly. And note that when you evaluate it, it's always just plus and minus 1. So it is the sine function. It's not amplified. Another way of saying it is you say the impulse has got to be equal to sine theta in order to get an amplitude of plus or minus 1. Again, we're back to this expression here. If you consider some other function, g of t, to be 2.5 at 48k, then g of t is this thing, 2 pi sine ft. So for the first sample, which is the impulse, t is 1/48,000th of a second. And so the first sample is this thing here, which is theta, 2.5, that's theta up here, that's this expression, radians per sample times 1 sample, you're just left with radians. And so that means that's just sine theta. So the impulse is going to be sine theta. And so it's going to look like, if you take 1 sample interval right here, starts at 0, but you give it an impulse, bam, sine theta. Initial position of velocity is 0, but the impulse of sine theta after 1 delta t, bam, up you go. The claim is that only one, 2.5 kilohertz sine wave goes through these points of the 2 points, t and t plus delta t. That one sinusoid has a peak-to-peak amplitude of plus minus 1. There you go. I spent a lot of time on that because people always ask that question. So aliasing, let's look at aliasing. Remember, again, from 113, when you sample a continuous waveform, what do? You end up with a repeating spectrum. The spectrum that it had in continuous land gets repeated at multiples of the sampling rate. So here's 30 kilohertz sampled at 96,000 samples per second. So there's a repeating spectrum at 96 and another repeating spectrum at minus 96. And this dotted line here, this is the anti-aliasing filter. This is, and I would stop it in a normal lecture. I would stop and say, what kind of, I think I do that in the next slide. Let's take a look here. Okay, there's the sample rate. This is the anti-aliasing filter. And I would ask, what kind of filter is this filter? And well, it is a low-pass filter, right? Even though it looks like it's a rectangle here, like it might be a bandpass, but no, it goes from 0 to 48 kilohertz. It also goes from 0 to minus 48, it's a low-pass filter. It does pass DC. It does pass DC. So, remember, go back to here, what is, and so what you're doing, you're in the frequency domain here, and what do? You multiply the spectrum by the filter transfer function, basically the transfer function. You multiply in the frequency domain. What do you do in the time domain? You convolve, right? You use convolution, and you use it with you do the inverse transform of the spectrum, which is a sine wave, and the inverse transform of this thing, which is that, sine x over x. And so you will do this. This is what you're doing in the time domain when you multiply in the frequency domain. And so you're taking this sine wave, sine x over x, and you're sliding it past all of those samples, which are just impulses, right? There are a whole bunch of impulse samples, and you're sliding it. And note that the delta t, if the sample rate is 1,000, the delta t is 1,000, and that means that the sinc function is 0 at every one of the samples where all these triangles are, except for the one where you're at, in time. There it's 1. So that gets multiplied, but look what's going on in between the samples, and that's what the interpolation is all about, right? It's filling in the time between the samples. It's filling in the time between the samples when you're sliding that sinc function by the impulses of the samples and multiplying them together. So all of this stuff that's got a non-zero value, as it slides by, you get a non-zero product. So anyway, and this of course also shows why you can't ever get it all the way back. Why? Because the sinc function is infinite in both directions. It never goes to 0. So, you can't ever get a complete perfect in the practical world. You can't. Theoretically, you can. Okay. I was pointing out the delta t is the same as the sample rate. So I'm just going to ask in an aside, when you take a DFT, what does it show? It doesn't show the spectrum centered on 0. It shows these two peaks. This peak is the plus frequency portion of the spectrum centered at 0, and the blue one here is the negative frequency portion of the spectrum that is centered at 96. That's what you see when you do your DFT calculation. You will see that it is a mirror image mirrored around the Nyquist frequency of 48 kilohertz, 48,000 samples per second. That's what you'll see. And again, this is the portion of the repeating spectrum that is calculated by a DFT. The words are what I just said. Another thing is that if you do this on an oscilloscope, you only see this much of it. You only see the left half, from 0 to the Nyquist. That's all you see. That's all you need to see, right? Because everything else is a mirror image of what you see here. So there's no new information for you. All right. So here's this. This is a MATLAB thing I wrote to show the difference between straight line interpolation and sine x over x interpolation. This is a 3 kilohertz signal that is sampled at 96,000 samples per second. It's well underneath the Nyquist frequency of 48, and yet look what straight line interpolation gives you. Doesn't look anything like a nice sine wave. But sine x over x, you get it back. You get it back. It's beautiful. And this is the FFT showing the single peak. The plot stops at the Nyquist frequency. All right. So here is another example of what happens when you are still following the sampling theorem, but not using sine x over x. This is a signal that is 23 kilohertz, and the sample rate is 48,000. That means the Nyquist is 24. So 23 is less than 24. But when you do straight line interpolation, it looks an awful lot like an amplitude modulated signal. And you can actually see this on an oscilloscope. You can actually see that on an oscilloscope. However, if you do sine x over x, it looks pretty good. There is some error at the tail, at the edge. There are edge cases right here, and the other end. It's not quite right, but in the middle, you get it. You know, you're losing a lot of the sine x over x function when you get close to the edge here, and that's why you're creating errors. So here is, I think that's the same as what I had before. Oh, okay. So this is kind of nice. You're going to need to do this. You should look at this because you're going to need to calculate what the scale is on the frequency axis when you do that. And so you can use this expression, this little analysis right here, to figure out what the scale is along this axis. I'll just leave that for you to take a look at and study. So here's what happens when you get aliasing from a spectrum standpoint. Here now, we've got the same 30 kilohertz sine wave, but now it's being sampled at 48 instead of 96. And so the Nyquist is 24 and the signal is 30, so it's bigger. And so now here is the anti-aliasing filter at 24, right? And note that the original spectrum centered at 0 is outside the range of the anti-aliasing filter. So what you're seeing again here is the negative component of the spectrum centered at 48, and this one is the positive component of the spectrum that is centered at minus 48. And that's what you're seeing. And this is not 30, which is out here. This is 30 is 24 plus 6. This point right here is 24 minus 6. 24 minus 6, so it's 18 kilohertz. It is 18. So this is why they call it aliasing. It's actually 30, but it looks like 18. It looks like 18. And this can be called, the Nyquist frequency can be called the folding frequency, or sometimes the mirroring frequency, or there are lots of different names for it. So there's your anti-aliasing filter. This is the signal that we actually see right here. And again, my analysis. Now, of course, the straight line is pretty awful, but so is the sine x over x. Look at that. The blue is the original 30 kilohertz. The green is what sine x over x tells you. And the peak, there's the peak. There's 15 kilohertz. There's 20 kilohertz. This is sitting right at 18. Right at 18, right? Where you would expect it to when you know about aliasing. And so here's even worse condition, and I'm not going to, I'll let you play around with that if you want. But it's even more egregious, I guess. And here is the peak at 6,000 now. It's a 30 kilohertz signal, and if you have aliasing, it looks like 6,000. All right. So I mean, you can do this with 3 lines of MATLAB code. You can show this. Here's 3 lines to get that sine x over x, that amplitude modulated thing. Just try it. You know, you're going from t to half a millisecond, 5 times, 5e minus 4. 0 to half a millisecond, 48,000 samples per second. And here's the function. It's a cosine function at 23,000. So Nyquist is 24, cosine is 23, and now we're going to plot it out. We're going to plot it with a line width, and we're going to have a red marker edge color. And this, what does this tell you? This tells you the B means it's going to be blue. The caret means it's going to be a triangle. The marker is a triangle. And the hyphen means that we're going to do straight line interpolation between the points. And when we do that, we get this. Again, your amplitude modulated signal. So you've followed the rule, right? You followed the the sample rate being twice the highest frequency rule, but turns out there's a second rule. This is a good interview question. According to the sampling theorem, in order to perfectly reconstruct the input analog waveform from samples, what 2 requirements must be met? Clearly, the sample rate being twice the highest frequency, and the second one is that sync interpolation must be used. And I'll let you take a look at this also. Clearly, what you've got on the x-axis is the actual input frequency, and on the y-axis is the apparent frequency when you sample. And as long as you are less than half the sampling rate, the input frequency is less than half the sampling rate, everything looks good. 45 degrees, just what you want. After that, not so good. And it just keeps bouncing back, and the signal never looks more to be higher than half the sampling rate as you go out there. All right. That's it. Okay, so that's the end of the lecture. So you can now, what we'll do is the TAs will have some things to say about what's going on with the experiment itself, and I will let them do that in the actual lab section. So thank you for listening, and I will end it here.